Hi, welcome to another video on PolyML. Today we'll be looking at higher order functions and how to use them. So what is a higher order function? In basic terms, a higher order function is a function that accepts a function as a parameter or can output a function as a result. So, for example, if we had the function to increment a number, higher order functions would allow us to put this function into our other function. So if we have another function, we'll call this high_fun. We will take a function as an argument, a value, and we'll apply that function to the value. To test this, we can simply just test our function. So we do high_fun, we'll give it inc as the function that we're going to give it, and we'll give it 1. Comes up as 2, as inc increments number once, and we've supplied the function and a value. So let's create something a bit more complicated. Let's create a function that adds all the numbers from a specified value below it after they've been applied the function that we will give it. So if we start off with fun, then we can do sum f, because it's a sum function, give it f, and because this will be recursive, we will start off with a base case of 0, and we use pattern matching. Next line, we can do sum f, we'll give it the function again, and then we can give it a value. And now what we want to do is apply this function to the value and then add it on to the recursive result of every number below x. So this would be sum f, we'll give the function again, and then we'll give it x minus 1. So to test it, we will need to create another function to give into the f value, so we'll create inc again, and we will apply inc into the sum f. So if we do sum f, then we call inc, and we'll give it, say, 3. What this is doing is it's taking x, which starts off as 3, incrementing it by 1 to 4, then it'll take 2, incremented by 1, 3, taking 1, incremented by 1, which is 2, and then taking 0, but 0's base case, so then it will return 0. And because it's recursive, it'll go all the way back up the line and go to 9. So this is just a very basic higher order function. But the beauty of this function and all the other higher order functions is that f can be any function. So if we created another function that divided by 2, or squared a number, or multiplied it, this would still work for this function, as long as the function you give it can be applied to the value x. So let's test this. Let's create a function that halves a number. So if we create the function half, we'll give it x. We'll take x and we'll div 2. So now if we take our sum f function, sum f, and we apply half to it, and we'll say 3 again, it comes out as 2. So 3 gets halved to 1.5, which would flow to 1 because it's an integer. And then 2 would get halved to 1 again, and 1 would go to 0.5, which would go to 0. So that would be 1 plus 1 plus 0, and that gives you 2. Another function we could do with this is to apply a function to every value of a list. So to do this, we'll start off with a simple function. We'll have f as the function we're going to supply it, and as we're going to be using pattern matching, we will have an empty list that supplies an empty list when there's no other values to apply the function to. The next line, we'll have list, we'll have the function, and we'll have the head and the tail. So what this function is supposed to do is to apply a function to every value of a list. To get to every value of a list, you must recursively call the head of the list all the time and supply the tail to the recursive call. So in this part, we'll be wanting to apply a function to the head instead of just taking the head itself. So we'll do the function in the head, and then we'll do the recursion. So we'll do list, then we'll apply the function again, and then we'll give it the tail. So to test if this works, we can recreate our increment function. So now we can increment every number of a list. So if we do list inc, and then we just make up a list, so we'll do 1, 2, 3, 4, it comes back as 2, 3, 4, 5. because the increment function has been applied to every value of the list. Some functions don't even need to make sense. But to show the use of higher order functions, we can make another one, which will be fun, and we'll call it list it. We'll take x, and we'll simply just put x into a list. So if we now put that into our list function, so we list, and then list it, and then give it the same list again, 1, 2, 3, 4, this comes back and it's added each of them values in the list into its own list. So far we've only looked at higher order functions where the function is the argument. But what about higher order functions that return functions themselves? To show how this works, we'll create a very simple function that returns a function. So we'll do fun, and we'll do high f for higher order functions, and we'll take 1. So now we want to return an entire function. So we can do fn x, and that can go into x plus 1. That there in between the brackets is a function, and it will return that if you do high f1. Of course, the error message that comes up now is saying that the matches are not exhaustive, because if we did high f 10, 11, 99, it would come up with an error because we have not pattern matched for anything else but 1. So to show how this works, we can simply just do high f1. This comes back with an it value, which is of type function int arrow int, which is saying that it is now a function because high f1 has returned our function. So to use this, we could do it, and then we'll do 10, and if this works correctly, it should come back with 11, because it is the function to increment x by 1 that it has returned. So let's create something a little bit more interesting. Let's create a function that, given a value, it will either divide it by 2 or times it by itself in the pursuit of finding 0, whilst also maintaining a count value so we know how many steps it's taken to get from the value given to find 0. So first we need to create the function. So we'll create the function retf. We'll take one value and we'll check if this value is greater than 0, and if it's not, then we want to return a function which will divide it by 2, because if it's positive we can just simply divide by 2 and start getting down to 0. So we return the function fn x, which goes into x div 2, so that'll divide any x number by 2, and if we don't have an x value that's over 0, then we want to times x by itself. So if we do fn x goes into x times x, that should mean that any x value that is less than 0 or 0 itself will give the function back that will times x by itself. So this is our higher order function that will return a function. What we want to create now is a function to use this function, so that any value is given, it decides within itself whether to give back function A, which would be divide by 2, or function B, which would be times by itself. So to do this, we'll start off normally. We'll do fun 0 because we want to find a 0. Then the base case can just be 0. So once we found 0, we'll just return 0 itself. Then the next line, we want to give it a value. And since we are trying to count the amount of steps it's taken, we'll do 1 plus, and then we'll do our recursive call. So in this part, what we want to do is recursively call the 0 function again. But inside the 0 function, we want to decide whether we want divide 2 or x times x. So we'll call our return f function, but we'll need to apply it to x first to return the function to use on the x we have now. So if we do x, then that's our entire function. So then we'll apply that function to x as well. So what this is doing is it's going in, it's getting our recursive call, it's then going into retf with x, whatever x might be, checking whether x is greater than or equals to 0, returning the function it decides, and then applying this to x, and then putting all of that back into the 0 recursive call to do it again. So every time this does one step, it'll do 1 plus, do all of that recursive function calling, and then 1 plus again until it reaches 0. And because x times x will always result in a positive number, it means that we will always get to x is greater than 0, so then dividing by 2 will always come back down to 0 as well. So to test if this works, we can simply use it on a single value. So if we do 0, then we'll do 10, it comes back with 4, because 10 divides to 5, 5 goes to 2.5, which would be 2, 2 goes to 1, 1 goes to 0, which is 4 steps. But to check if the other half works, or to check if it's deciding which function to use, we can do 0, and we can give it minus 10, which comes back with 8, because that would be minus 10 times minus 10, which come to 100. 100 goes to 50, 50 goes to 25, 25 goes to 12, 12 goes to 6, 6 to 3, 3 to 1.5, which is 1, and then 1 goes to 0.5, and then it's 0. So it returns 8 steps. In this video, hopefully you now understand what higher order functions are. Functions that accept functions as parameters, and functions that return functions as results. And hopefully you understand how to create higher order functions yourself.